So for today's lesson, you may want to jot down some of these perfect cubes especially. We're going to be factoring a difference of perfect cubes. So if you notice the chart obviously is in order from 1 through, I'm not sure how high it goes on the squares, but for the cubes you'll only need to know up to 10. The quartix and quintix you can jot down. We're not going to be using those today, but we may see them in the future. So I'll scroll down if you want to check out the perfect squares. You should know some of the higher ones. So here we've got, hopefully you have up to 15 memorized. This is 15 squared. And then we've got 16 squared, 17, 18, 19, 20. And then it jumps to 25, 30, 40, 50, and then hopefully you're seeing a pattern and you'd be able to figure out 60 squared and so on. And I will scroll back up one more time in case you didn't get the lesson paused to get the first couple. So again, we're focusing on the perfect cubes for today. All right, two different factorings that we're going to be looking at today. First is difference of perfect squares, which we've seen before, so this should be a review. So the generic form is x squared minus a squared, and you factor it to x plus a, x minus a. If you have any coefficients, they need to be perfect squares as well, and then you just factor it very similarly. Sum or difference of perfect cubes. This formula looks a lot worse than it is. Once you practice factoring a sum or difference of perfect cubes a couple of times, you'll kind of see that there's a pattern, and it's not too bad. So we start with x cubed plus or minus b cubed, and then we take the cube root of each of those pieces. So if we started with x cubed plus b cubed, we would factor it to x plus b. So notice here, you keep whatever sign was on your original binomial, and then you just have the cube root of each of the terms. When you get to the second part of your factoring, now right here when it says first term or second term, we're talking about this binomial. So these are now our first and second terms. So we take the first term squared, or x squared. Here, notice we now have the opposite sign. So if we started with x cubed plus b cubed, now we're going to have x squared minus abx. And actually that a shouldn't be there. I modified this a little bit. So this would just be the first term times the second term. This is always plus regardless of the sign you started with, because we're adding b squared. Once you square negative, it becomes positive. So that last symbol is always a plus sign. And I will erase this in case you didn't get all of that down and you want to be able to read it. All right, so there's the formula again. Make sure that you get that in your notes. You're going to want to be able to have that to refer to. So we're going to start by checking to see if a binomial is a factor. So this is checking with synthetic division. So a little bit of review from what we did yesterday. Remember, we take the opposite of what's inside the parentheses. So -1. And then we use the coefficients from the polynomial we're dividing into. So 1x squared minus 3x plus 1. Bring down the first term, multiply by -1, add, multiply by -1, add. Remember that last piece right there tells you whether or not you have a remainder. In this case, we have a remainder of 5, so x plus 1 is not a factor of x squared minus 3x plus 1. This one's a little bit different. Yesterday I told you we can only use synthetic division if our x term has a coefficient of 1. This does not. However, when we look at the whole binomial, it has a common factor. So I can factor out a 2, and now I can check if x minus 2 is a factor of the polynomial. So that's what I'm going to do. So this -2 goes on the outside as a +2. My coefficients are 2, -4, 0x cubed, 2, negative 2, negative 4. Bring down the 2, times 2, add, times 2, add, times 2, add, times 2, add, times 2, add. So again, my last term right here, because it's a 0, it means there is no remainder. So 2x minus 4 is a factor of the polynomial. Difference of squares review. So this was one of those formulas that we just saw. So on this one, 49 is a perfect square, 64 is a perfect square, and so are a squared and b squared. So we've got the square root of 49, the square root of a, plus the square root of 64, the square root of b, and then we repeat, only the sign becomes opposite. So as a quick review, just to remind you why this formula works, when we FOIL this back out, 7a times 7a gives me 49a squared. 7a times negative 8b gives me negative 56ab. And then here I get a positive 56ab, so that middle term cancels. And then 8 times negative 8 is negative 64b squared. So the middle term cancels, leaving us with the 49a squared minus 64b squared. Taking a look at our second example, 3 and x cubed and 300 and x are all not perfect squares. But I do notice that both of these terms have a common factor. So I'm going to factor out the 3x, leaving my first term with an x squared, and my second term is minus 100. Now, x squared and 100 are both perfect squares, so I can keep factoring. The common mistake is that students lose that greatest common factor. So in this next step, I'll commonly see x plus 10, x minus 10 without the 3x in front. So make sure that you do not lose your common factors. Anytime you take out a common factor, keep factoring, but bring that common factor along. A little bit more review of factoring. Always, when you're factoring, look for a greatest common factor first. So I'm looking through and I see all of my terms have an x. So I'm going to factor out that x, leaving me with x squared plus 8x plus 15. Always check to see what's left inside the parentheses if you can continue factoring. Well, this one is a t-table factoring. What multiplies to 15 and adds to 8? Positive 3 and positive 5. So x plus 3, x plus 5. Second example, I'm looking through all 4 terms. I do not see a common factor on all 4 terms. So I'm going to try factoring by grouping because it's a quadnomial. So my first 2 terms, I see a common factor of x squared, leaving me with x minus 3. My second 2 terms, I see a common factor of 4, but the signs would be opposite from what I just got in my binomial. I'd have a negative x plus 3. So I'm going to factor out a negative 4 in order to have a positive x minus 3, so that I've got another common factor. Factor out that x minus 3, leaving me with x squared from the first term and negative 4 from the second term. Always check to see if you can keep factoring. I can't factor x minus 3, but x squared minus 4 is a perfect square binomial. So that's x minus 2, x plus 2. Now we're going to get into the new material, difference in sum of cubes. So the first thing that you're going to want to identify when you're factoring a difference or a sum of cubes is what's the cube root of each term. Well, obviously the cube root of x cubed is x. And if you remember from your chart, or maybe this is one you have memorized, sorry, I'm going to fix that. Calibration's off a little bit. So the cube root of 216 is 6. So x minus 6 becomes your binomial. And then the pattern, now I'm going to look at my x minus 6. I'm done with my x cubed minus 216. So when I'm filling in my second factor, I'm only looking at that x minus 6. So my first term is my first term squared, so it becomes x squared. Now I take the opposite sign from what I just have. I have an x minus 6, so now it's plus. I multiply my 2 terms together. X times 6 is 6x. And then my last term is plus 6 squared, or 36. Now you should always check to see if you can keep factoring. However, with the formula for the difference or sum of cubes, that second trinomial that you'll end up with will never be factorable. There's nothing that multiplies to 36 and adds to 6. So we're done. All right, for B, again, 27 is a perfect cube, and so is 512. So the first thing I'm going to do is identify the cube root of each term. Cube root of 27 is 3. Cube root of x cubed is x. Keep the sign. The cube root of 512 is 8. So that's my first binomial, the first step in my factoring. Next step is first term squared. So I'm going to take 3x squared. Be careful to square the 3 as well as the x. So it becomes 9x squared. Opposite sign. Multiply the two terms together. 3x times 8 is 24x. And then square the second term, plus 64. All right, my next example, 24 is not a perfect cube, and neither is 3, but I do notice they both have a common factor of 3. So I'm going to factor out that 3, leaving me with 8x cubed plus 1. Don't forget, when you're factoring, it means you're dividing. So this 3 divided by this 3 gives you this 1. Sometimes people forget that second term. All right, looking inside, 8 is a perfect cube, so now I've got a sum of cubes, so I can keep factoring. Don't lose your 3. Cube root of 8 is 2. Cube root of x cubed is x. And cube root of 1 is 1. And my second factor, 2x squared is 4x squared. Again, don't forget to square your coefficient. Opposite sign, multiply your two terms together, 2x times 1. Plus 1 squared. Last example. Same problem. 2 is not a perfect cube, neither is x to the 4th, so we're going to look for a common factor, which is 2x. Leaving me with x cubed. 128 divided by 2 is 64, which is a perfect cube. So again, bring down that common factor, don't lose that. Cube root of x cubed is x. Keep the sign. Cube root of 64 is 4. First term, x squared. Opposite sign, x times 4 is 4x, plus 4 squared is 16. Hopefully after 4 examples, you started to see the pattern and you're not quite so scared of factoring perfect cubes.